Welcome to a new video heat transfer. Today we continue our discussion of heat exchangers, and we talk about another method to design heat exchangers. It's called effectiveness NTU method. In the previous lesson we presented the LMTD method, the log mean temperature difference method. It was useful to find the surface area of a heat exchanger. Therefore, we could find the size of heat exchangers if we knew the four temperatures that characterize the heat exchangers. That is, the two inlet temperature and the two outlet temperatures. And also, if we knew the heat transfer that we had to exchange between the two fluids. But now we present another design method, and the objectives now is to design the heat exchanger without knowing the outlet temperatures. Although we know the mass flow rates of the hot fluid and the cold fluid and the inlet temperatures. For this problem, we could still use the log mean temperature difference method, although an iteration would be required, so that's not really convenient. Instead, the effectiveness NTU method is based on the heat transfer effectiveness, epsilon, and that's defined as the ratio between the actual heat transfer exchange between the two fluids and the maximum possible heat transfer that could be achieved for those mass flow rates and inlet temperature difference. The actual heat transfer is the same for the two fluids because we work under the assumption that no heat is exchanged to the outside, to the environment, so there's no loss of thermal energy. So Q is equal to big C with underscore C, that's a heat capacity, so m dot C CPC of the cold fluid times the temperature difference. That's the cold fluid experiences, so the Tc out minus Tc in, that's equal to the heat capacity of the hot fluid times the temperature difference experienced by the hot fluid, that Th in minus Th out. The problem now is to find the maximal heat transfer rate that's possible to be exchanged between the two fluids. The Qmax is equal to the C min, so the heat capacity, that's the smallest one between the two fluids, times the difference between the two inlet temperature that are known for our case, so Th in minus Tc in. So this temperature difference is the maximum possible jump, and that occurs when the cold fluid reaches the inlet temperature of the hot fluid, and also when the hot fluid cools down to the temperature of the inlet temperature of the cold fluid. So this is the maximal possible jump that can be achieved by either of the two fluids. And it's important to remember here we need to multiply by the heat capacity that's of the smallest one, because the lesser jump in temperature is experienced by the fluid that stores less thermal energy. We need to keep in mind that m dot C times the specific heat capacity, so there is of course an expression, a quantity that defines how much energy is actually stored. So to achieve the largest possible jump in temperature, that fluid must store as little heat as possible. So therefore, if we know the maximum heat transfer that can be exchanged between the two fluids, and we know the effectiveness, then we can compute the actual Q. So we arrange the previous expression. So the actual heat transfer Q, the exchange between the two fluids, it's equal to effectiveness times C min times the jump in temperature at the inlet of the two fluids. It's important to remember that thanks to this expression, there is no need to know the outlet temperatures. So the next step is to find a method to compute the effectiveness. So for simple cases, We can do some mathematics just like when we did for the log mean temperature difference method, so some energy balance. So for simple heat exchangers, we can find an analytical expression. For example, here for a parallel flow heat exchanger, we see epsilon has this form. And what's interesting to note is that there are two quantities that can be noticed here in the formula. We can see that the effectiveness depends on two quantities. One quantity is what we call NTU, the number of transfer units. That's U, the overall heat transfer coefficient that we computed in the last lesson, times AS, the surface area, divided by the smallest C mean, so the smallest heat capacity. And then we have small c, and that's the ratio between the two heat capacities. So in general, the effectiveness epsilon for a heat exchanger is a function of these two quantities. So to compute effectiveness, we can just use the formulas that we can find in many books of heat transfer. But a quicker way, although less accurate way, is to use charts where those formulas are plotted, and they usually assume this kind of form. So here on the y-axis we have in percentage the effectiveness, and on the x-axis we have the NTU, the number of transfer units. So for different heat capacity ratios, we have different pink lines. All we have to do, we have to compute the NTU that we remember. This is U, the overall heat transfer coefficient, times the surface area divided by the smallest heat capacity. So once we compute this quantity here, NTU, and then we move up and we stop at the line that corresponds to the ratio of heat capacities that we need, and then we move to the left and we compute the percentage that we need. We can compute the effectiveness of the heat exchanger. So a few comments on the plot that we just saw. The effectiveness in percentage is always between 0 and 100%, and it grows quickly with NTU from 0 for small values of NTU, but then it grows more slowly for larger NTUs. Of course, one might think that the larger the NTU, the better, because we achieve a larger effectiveness. This is true in theory. So for heat exchanger design, although we need to take into account also economical reasons. So if NTU is too large, this means the AS, the surface area, is too large, and then the heat exchangers become too large and then economically not viable. And the other thing to note is that for small value of NTU, the effectiveness does not depend on the heat capacity ratio. As the final observation is that the heat capacity ratio is always in the range between 0 and 1. And so for fixed NTU, the effectiveness grows as the ratio drops. So in summary, if we want to design a heat exchanger, it depends what we want to achieve. If we want to find the size of our heat exchangers, then we use the log mean temperature difference method. In these cases, all the 4 temperatures must be known. So we must know the inlet temperatures and the outlet temperatures. Instead, if we only know the inlet temperatures and we want to find the actual heat transfer exchange between the two fluids, then we use the NTU effectiveness method. And in this case, the AS must be known. Okay, thank you very much. I'll see you next time.